So let's begin with the discussion. So based on the input and the output data and a specific algorithm, we basically try to model a plan, that is the system identification, wherein we try to mathematically model the plant using either the transfer function or the state space equations. And then once the plant is modeled, we try to predict the output based on the plant and the input data. So this is what is the system identification. Then there's a term learning, which basically it the system it kind of learns from the error. The system responds to the input to get the desired output based on the error. Then uh, then Amit, you can begin.
Yeah, then I think we can move on to the prediction phase. Basically, what we are trying to predict is we are trying to see how far away we are from the value that we have predicted and what is the actual behavior of the system. So, in case, just think of it as a car moving on a road. So we don't really know where the ridges and grooves are, but we expect the car to move an x distance. But if there is a speed bump, then the distance that we have moved is actually more than x. It would be x plus delta x. So that is what we are trying to predict using the prediction algorithm, and then we are trying to take in all the data, and then we are trying to fit it in a particular curve so that we can actually predict how the future values are going to behave. So that is what is called regression. And in regression, if the data points are finite, and if then we can use the least squares method to actually estimate the value of a and b. Say we are giving the straight line equation as y equal to ax plus b, then in that case we can actually evaluate the values of a and b using the recursive least squares estimation. So a little bit of insight into recursive least squares is that, see, errors can be positive errors, errors can be negative errors. So what the least square errors is trying to do is we are trying to normalize all the errors into the positive side. So by squaring them, what we are trying to do is we are trying to find out the error of the curve from the positive axis itself. Because error is an error, even though if it is a positive error or the negative error, the error is going to be the same, right? I mean, like, the error value is an erroneous value that we don't want in the system. So by squaring the values of the error, what we are trying to do is we are trying to find out the perfect fit in such a way that the least square the we are trying to minimize the value of the squares of the errors in such a way that the curve is actually fitting all the data points and satisfying all the necessary points. And then you can take it on.
All right. Amit has told about the least square estimation, in which, for example, we have some thousand. There is a system which has about 1,000 inputs and around 100 outputs. Consider we have the x as the input and y as the output. So if you consider like m as the number of inputs, the 1,000 inputs, and we have the 100 number of outputs, let them be y. So if we are trying to get the output yj, it might be like a1j into x1 plus a2j into x2 plus etc. until xm. So we have like thousands of parameters to be found out just for finding the output value yj. But this normally we find the parameters using some inversion method. So it will be complex to have all these 1,000 parameters and identify them.
What
So
exactly is an inversion method?
meaning we have y equals ax.
Yeah, yeah.
So a is the parameter. Then if
Hmm.
you want to find a, we'll find the inverse of it. Means
Oh, acha, acha. Yeah, yeah, got it.
but as I just told, this input space, if it is the number of inputs are high, the input space will be too huge and
Yeah.
too computationally intensive. So we'll do something like extracting latent variables. That means even though we have some 1,000 inputs, we'll extract some significant inputs which will actually affect the output. So such kind of, Amit, you want to ask something?
Yeah. So say
Hmm.
now, like you have mentioned, there is a set of outputs and there is a set of inputs.
Yes.
How do we actually evaluate which parameter is important for us to get the output? Is it from the confidence interval, or from what do we actually determine all that?
So here basically we are finding the eigenvalues and eigenvectors. On the basis of that, we decide which is more
There are
significant and which
some
is less
methods
significant.
to find the latent variables or the hidden variables which
Hmm.
actually affect the output.
Okay, okay, okay. So we are trying to club them together and make it into like one single entity.
No, meaning if we have thousands and if
Huh.
only 100 actually affect the output, we'll
Huh.
take only the hundreds. So that's,
Okay, okay. So the other ones are shunted off.
yeah, they are not
They are
significant
ignored.
for the
Yeah.
output.
Hmm. Okay, okay, okay. Okay. Nikita, you can continue from there.
Yeah. So basically the problem with this method is that there are large number of data which we need to look into. So instead what we try to classify them into significant and less significant by finding the eigenvalues and eigenvectors correspondingly. So the significant is so we actually modify the input space by calculating the eigenvalues, and then if the original input space is x1 x2 up to xm, then after modification the modified input space is z1 z2 on so
Okay.
on till zm star. So based on this z1 and z2 as inputs, we predict the output y1 y2 like yj, which is equals to bj1 into j1 plus pm star, and so on up to bm star into jm star.
Okay, okay. So one doubt that automatically comes here is that the eigenvalues that we are trying to focus on here, what exactly is like the behavior of the eigenvalues? Like in analyse yesterday we have studied that the decay time is faster if the eigenvalue is greater.
Hmm.
Okay, so there is a faster decay and then there is a slower decay time.
So
Okay, so in this case, are we trying to say that the higher the eigenvalue, the lesser effect it has on the system?
No, no, I guess it's the other way.
other
If
way.
it is having a higher eigenvalue, that means it's more significant.
Okay, but what I have written in my notes is that with a large value with a large value coming in the eigenvalue set, input is not
Lesser than,
significant for
yeah, that
predicting the
means
output.
That's
actually the first method is checking it this way.
Hmm.
They thought that if we have a higher eigenvalue, that would
Okay.
be contributing more. But
Okay.
they found that it might not be actually
Oh.
necessary that the one with higher eigenvalue will contribute more.
Hmm.
So
Okay.
this method is called partial least square regression. No,
uh,
not that. The one before that. What is it? Principal component
principal
regression.
component regression.
Yes.
Oh.
That's where
Okay.
we check the eigenvalues and found that it would contribute more. But as they found that it is not so, they went for the next method. That is the
Okay.
partial least square
Partial
regression.
is for regression.
Yeah. So in this case, say we have m number of inputs. After extracting the significant variables, the number of inputs would drastically reduce to
Reduce.
m
Yeah.
star.
That's what we want.
Yeah, so m star is lesser than m,
Yeah.
Yes. Very much less than
and
m.
yeah, and using these m star input values for the regression set, we
Hmm.
are trying to predict y values, right? The
Yes.
output values.
Yes.
Hmm.
Okay.
That's the whole
Okay.
idea of estimation. We'll
Huh.
have some data set. With the
Huh.
data set, we will get the new value. It might be prediction, it might be classification or identification and so on.
Okay, okay. So let's move ahead to recursive estimation. So now that we have plenty of data, I mean, we what we have discussed so far is that we are assuming that we have a lot of data available with us already. But in a real-time system, it may not so happen that we have the data with us in for ready to perform the data analysis on. So say in a system, we get for a real-time system, we get the data at each time interval. So as the data keeps coming in, the curve keeps changing. It's not necessary for us to actually evaluate the entire values of a and b all over again, but we can just find out the value delta x and delta a and delta b in order to make sure that the curve is still fitting the values that are coming in through the system. Uh, what do you take on? I mean, what is your take on this method? Say the data is coming in dynamically, but then by just evaluating the value of delta A and delta B, are we really able to cater to all the values that are coming into the system?
I guess we are updating the values of A and B by
Yeah.
comparing the estimated value y cap with the actual output.
Okay.
So this the recursive least square estimation or regression actually is in considering the noise in the system, be it process noise or measurement noise.
Hmm.
So this
Okay.
method, recursive least square regression, was developed by like Gauss in some 18th century, I believe, and some
Yeah.
century ahead, Kalman devised this method called Kalman filter, in which they would consider noise as well.
Yeah, so I can give you an example of this where recursive method is used.
Yes.
Actually, last semester we had a subject called adaptive control theory in which we studied something called model reference adaptive control. So I'll give you the gist of what exactly happens in the system. So we want a system, we want a certain plant to behave as a certain plant. So uh, one is the plant that we have, the other one is a model that it has to behave as. Okay, so for the model parameter, we know what exactly the matrices are, A, B, C, D matrices, and how it exactly is performing. That is all known to you. Okay, but you want a certain function or a certain plant to behave as the model. Okay, so in that case, what you need to do is you want to frame your update loss in such a way that you're able to track whatever the model is doing. So say the model would react a certain way for a certain input. Okay, now you want to now you want to mimic the same for your plant as well. Now you how you do that is you keep changing the control law at each time interval based on the values that you're getting previously. You update your control law, and from that control law it is actually learning. This uses recursive least squares estimation. So
But
it
I
is
have a
finding.
like, clarification as well. Are we updating the control law or the parameters also of the system in this method?
Yeah, so there is direct MRAC and indirect MRAC. So first we in direct MRAC what we do is directly we change the control law. In
Hmm.
indirect MRAC first we estimate the parameters, and from the estimated parameters we are trying to update the control law.
Okay, so we
So
have both, like at
both the methods
the
use MRAC.
parameters as well as the control law.
Yeah. So this is where it was earlier deployed, and yeah, because this is a relevant example, I feel like pitching it in here.
Hmm. It was also mentioned that this was used in the Apollo mission for
Uh,
Yeah,
Prof.S destination tracking.
yeah, yeah,
so Amit, what you told him that was indirect adaptive control. What
yeah.
you just explained.
It's no, actually, it is a direct adaptive control because here we are not dealing with estimating the parameters first. We are trying to update the control law directly. See, indirect control is much more easier than direct control because indirect control first we estimate the parameters, and based on the parameters we plug in the values of the estimated parameters, and then we are trying to update the control law.
Okay.
But in the direct model, what we are trying to do is without estimating the parameters, we are trying to update the control law. So the complexity is at a place where without knowing what exactly is happening to your A matrix or B matrix. I mean, if you see the equations in the control law itself, there will be bounds on B matrix. Where B
Hmm.
can go, where B cannot go. So because all this is not taken care of because you are not estimating the parameters, direct control becomes a lot more tougher than indirect control. Yeah,
Okay, got it. Hmm.
yeah. Next, moving on to
Random variable.
yeah,
Random.
random processes. Okay, so then here we have uh, if a process noise is uncontrolled, then basically it may produce unwanted or undesirable situations in the output. So what we predict may not actually be what we want the output to be. So we can take an example of the active noise cancellation in mic in a earphones. So this microphone is actually taking signals from the outside, but because this is a disturbance in the process, it should also take in what I'm speaking. It is also taking in what the background is giving it, but actively it is trying to cancel out the noise component, because noise component doesn't have a particular tone, particular amplitude. It comes just randomly. So it is trying to avoid all this, and it is trying to keep the signal from the noise, away from the noise. So a lot of noises can enter into the system. There can be feedback noise, input noise, output noise. All these noises, they can enter into the system. But what we are trying to do is we are only trying to minimize the input noise in case of a headphone, I can say.
I think in the other video, Professor Mukhopadhyay had added one point, like in this active noise cancellation,
Hmm.
actually we are trying to estimate what noise will arrive and then send an anti-phase signal which would cancel this noise.
Oh, okay.
That was there in the other video.
Hmm. Okay.
All right. So
Yeah.
then, yeah,
Then you can take it on to Kalman and base filters, and then we can end it there.
yeah. So this Kalman filter, we had the noise as the Gaussian noise, but in Bayes filter, we could have both non-Gaussian distribution as well as non-linear dynamics as well. Actually, Kalman is a special type of Bayes filter in which you have only linear dynamics and Gaussian distribution.
So what exactly is the Gaussian distribution doing here with respect to noise?
No, I'm not very sure about that.
Okay. So
Yes, we have
from what
classification
I have
noise
understood,
rings, one which has the graph similar to a Gaussian distribution. I'm not very sure, something of that sort. And
hmm,
if the noise matches a Gaussian distribution, this will work, and so on. But I'm not
okay.
very sure of the answer.
So the noise is actually supposed to follow a specific distribution,
The
and
noise,
only
yes, if the noise follows this distribution, then this filter can work. If it does not,
okay.
then that's what my understanding is. Nikita, would you like to add on?
Yeah. So here later they have discussed that as we increase the number of data points, the distribution goes on becoming narrower. So we get a perfect, like not perfect, but kind of a better estimate of the parameters.
Better as well as faster.
Yeah, and the convergence rate is faster. Yeah,
Yes, yes.
yeah,
Okay,
And
okay, okay.
selection of inputs also is dependent upon this Gaussian distribution.
Okay. So
And
from my understanding, the way Kalman filter works basically is it will from the model it will try to see how much the noise exactly is, and then it will try to attenuate the gain of the noise so that the noise component is actually lower than the signal that we desire in the output. Right.
okay.
Okay. So then they have given something as a correction factor which is proportional to prediction error by confidence of previous estimate into number of the variance.
and yeah, yeah.
Yeah.
The and later on it was discussed about the inputs which can be given for system identification also. There
Yeah.
there are some signals like sinusoidal signals,
Hmm.
then chirp signal, that is sinusoidal signal with increasing frequency, and also PRBS signal, the pseudo random binary signal. It is found that if you use these signals, we'll be able to get the system identifier or the parameters faster, and noise as well will be reduced.
Yeah.
Okay. Yeah. I think we can stop our discussion here. That should be enough.
Yes.
Should I stop the recording?
Yeah, you can.
Yeah.